For years, building models that understood sequences, like language, meant processing them one step at a time, or using very specialized structures. This paper asked a radical question that changed everything.
When you say one step at a time, you're talking about RNNs, right? The ones we covered in hashtag TCM003002, where each word's understanding depended on the previous word's hidden state?
Exactly. Before 2017, the state-of-the-art for tasks like machine translation relied on what the authors call complex recurrent or convolutional neural networks. They were powerful but slow.
Slow because of that sequential dependency, I guess. You can't compute the hidden state for word 5 until you've computed it for word 4.
Right. Even with attention, which we covered in TCM 003002, helping models focus on relevant parts of the input, the underlying structure was still recurrent. Attention was an add-on.
So attention improved them, but it didn't fundamentally change how they processed sequences. It was like putting a turbocharger on a car with a sequential gearbox.
A great analogy. Now listen to this. We propose a new simple network architecture, the transformer, based solely on attention mechanisms. That's the core idea right there.
Solely on attention? So no more sequential processing, no more hidden states passed from word to word? That sounds like a massive shift.
It was. This was the revolutionary part, dispensing with recurrence and convolutions entirely. This means every part of the input can be processed simultaneously, not sequentially.
Wait, we talked about the transformer's parallel attention mechanisms in hashtag TCM123001. Is this the why behind that? The ability to parallelize?
Precisely. The consequence of ditching recurrence is stated directly. It makes models more parallelizable and requiring significantly less time to train. This is the huge practical benefit.
So the question they answered was, can we build powerful sequence models that can train much faster by leveraging modern parallel hardware? And the answer was yes, using only attention.
And the results proved it wasn't just a theoretical win. Our model achieves 28.4 Blue on the WMT 2014 English to German translation task, beating prior state-of-the-art.
Outperforming models that had been refined for years and doing it faster. That's a strong statement. It's not just a simpler architecture, it's better too.
Absolutely. And it wasn't a one-trick pony for translation. They showed the transformer generalizes well to other tasks, like parsing, right out of the gate.
I can see how powerful this idea is now. It's not just about speed, it's about a foundational shift in how we approach sequence modeling.
Exactly. So, how does this attention-only structure actually work? How can it process an entire sentence at once and still understand context without sequential memory?
I'm ready for that. My brain still wants to connect things sequentially. Let's see how they broke that dependency.
This amazing post, the illustrated transformer, helps visualize how. The key insight is that instead of processing word by word, the transformer processes the entire input simultaneously.
So if an RNN is like a bucket brigade passing water one bucket at a time, the transformer is like an overhead sprinkler system, watering everything at once.
That's a fantastic analogy. That sprinkler system approach is why it lends itself to parallelization, making it incredibly efficient on modern hardware like GPUs.
But if it processes everything at once, how does it know the order of words? An RNN inherently knew order by processing sequentially.
That's where positional codings come in, which we discussed in hashtag TCM153001. But structurally, it still has the familiar encoding component, a decoding component, like many seek-to-seek models.
Okay, so the overall task division is familiar, but the internal mechanisms are different. Instead of a single complex RNN for encoding, what do we have?
Inside, instead of one giant encoder, we see a stack of encoders. Each one refines the representation of the input, passing its output to the next encoder above it.
So, multiple layers of processing, like a deep neural network, but each layer is an encoder? And these encoders don't share weights, even if they have the same structure.
Correct. And each one is broken down into two sublayers. The first is what we're really focusing on today, the self-attention layer.
Self-attention. We heard that term in TAC M123001. This is where the model looks at other parts of the input to understand a specific word, right?
Yes, a layer that helps the encoder look at other words in the input sentence. Think of it like this. For every word it asks, which other words in this sentence are important for understanding me right now?
So, it's not waiting for information to flow sequentially. It's like each word shouts its question and all other words respond instantly, weighted by relevance.
That's a perfect image. The output of that self-attention is then fed to a feed-forward neural network. This part processes each word's new, context-aware representation independently.
Independently, but still in parallel. So the heavy lifting of context gathering is in self-attention, and then the feed-forward part does its own local processing?
Exactly. The author notes, there are dependencies between these paths in the self-attention layer. The feed-forward layer does not have those dependencies. This is crucial for parallelization.
So, the self-attention creates the context, but because it looks at all words at once, it's parallel. Then the feed-forward network processes those context-rich representations also in parallel.
You've got the high-level intuition. Now let's zoom in on that self-attention layer. How does it actually figure out which words are relevant to which other words in a sentence?
That's the magic trick. How does that asking and responding system actually compute a meaningful context without any recurrent connections?
Let's take a classic example. The animal didn't cross the street because it was too tired. When the model sees it, it needs to know what it refers to. To a human, it's obviously animal, but for a machine, it could technically refer to street too. This ambiguity is what self-attention helps resolve.
Exactly. The core mechanism starts by taking each word's embedding, its initial vector representation, and creating three new vectors from it: query, key, and value.
So, for each word, say animal, we get an animal query, animal key, and animal value vector. These are just linear transformations, like we saw in other neural networks.
Right. As the paper says, these are the query vector, a key vector, and a value vector. Think of query as asking, what am I looking for? Key as, what do I have to offer? And value as, here's the information I carry.
That analogy helps a lot. So, to figure out what it refers to, it would have its own query and then compare that query to all other words' keys.
Precisely. The next step is to calculate a score. This score determines how much focus a word, say, it, should place on every other word in the sentence.
And how is that score calculated? Is it just a simple comparison?
Yes, it's elegantly simple. The dot product of the query vector with the key vector of the word it's comparing against. A high dot product means high similarity, high relevance.
So, its query vector is dot producted with animals key vector and streets key vector, Whichever yields a higher score is more relevant.
Correct. After scaling to prevent gradient issues, these scores are passed through a softmax operation. This normalizes them into probabilities that sum to 1.
So if it gets a 0.8 score for animal and 0.1 for street, it truly attends more to animal. This is how the model quantifies relevance.
Often, yes. As the author notes, clearly the word at this position will have the highest softmax score for itself, but the magic is in the attention to other words. It's like looking in a mirror, but also looking around the room. The mirror might be clearest, but the room gives context. Then, each of these softmax scores is multiplied by the corresponding word's value vector. Finally, you sum up the weighted value vectors to create the output for the current word.
So it takes 80% of animals' information, 10% of streets' information, and so on. Its new representation is a blend of all relevant words weighted by their attention scores.
Exactly. This is what we meant in TCM 003002 about attention dynamically weighing information. Self-attention extends this, allowing every part of the input to weigh every other part simultaneously.
This makes sense. Each word's output is an informed blend not dependent on previous hidden states. This is how it achieves parallel context. So where does this idea go next?
After attention is all you need, the transformer architecture has become the de facto standard for natural language processing tasks. It proved its power beyond doubt.
From what we just saw, it makes sense. The parallelization, the powerful contextual understanding, it's a perfect fit for language.
But for years, its applications to computer vision remain limited. People thought convolutions were indispensable for images because they naturally capture local features.
Yes, CNNs excel at recognizing patterns like edges and textures locally. A pixel-by-pixel self-attention on an image seems computationally massive and potentially less effective.
That was the prevailing wisdom until this paper. They showed a pure transformer applied directly to sequences of image patches can perform very well for image classification.
A pure transformer? Without any convolutions? That's as radical for vision as the original transformer was for language.
Indeed, the title itself, "An image is worth 16 by 16 words," explains the core trick. Instead of individual pixels, they treated image patches as words in a visual sentence.
So they tokenize the image. Just like embedding words into vectors, they embedded image patches into vectors. Then self-attention could work on these visual tokens.
Exactly! This vision transformer, or VIT, then processes these patch embeddings just like a language transformer processes word embeddings, and it attains excellent results.
This confirms what we touched on in CTCM 21302. The transformer's sequence processing capabilities extend naturally to images by treating them as sequences of patches.
Yes, and the key was its ability to scale. When pre-trained on large amounts of data and transferred to multiple mid-sized or small image recognition benchmarks, VIT shone.
It means the general-purpose attention mechanism learned incredibly rich visual representations from sheer data volume without needing specialized convolutional biases.
And the benefits were analogous to NLP. It performs well compared to state-of-the-art convolutional networks while requiring substantially fewer computational resources to train.
Fewer resources to train? So parallelization for the win again. This is the core strength that carries over from language to vision.
Absolutely. This idea taught us that the fundamental mechanism of attention is far more universal than initially thought. It's not just for language. It's for any data that can be broken into a sequence of tokens.
So whether it's words, image patches, or even audio segments, If you can turn it into a sequence of vectors, the transformer can model it. That's incredibly powerful.
And that's the core mental model for the transformer. It's a parallel attention-only architecture that leverages the query key value mechanism to build deep contextual understanding across any sequential data type.
I'm Maya. Thank you for thinking this through with us.
I'm Margin. Another idea in 3 hours. Take care of your mind.